Hello grade 12s, welcome to my channel. I hope you guys are good. Unfortunately guys, we couldn't have our tutorial this evening, so I decided I'm going to drop some shorter videos for you guys to keep working, and then we will have our tutorial tomorrow. Alright, so I just finished my case. It's one of the long ones. So yeah, tired as I am, I felt let me just drop something to keep you guys busy. Because I know you guys don't sleep anyway, even if I tell you to sleep. But please guys, refrain from not sleeping, especially the night before the exam. You need to rest your brain so that you can use it effectively. Great, we're going to take this November 2018 Physical Science Paper 2. And we're just going to treat the MCQs for the first stint. And then of course, we're just going to take some questions sequentially, individually, so that they can be available within reasonable time for you guys to use. Now we're going to treat these MCQs. Okay, so of course various options are provided as possible answers to the following questions. We then choose the answer and write only the letter A to D next to the question number in the answer book as illustrated here. Okay, great. So first question says, which one of the following is the structural formula of the functional group of ketones? Now this is a lower grade question. It's either you know or you don't. And of course it's option C. Now if you don't know this, please, this is an invitation to go and check the functional groups in terms of structural formulae of each of these homologous series. But if you know that this is comfortable for you, check, you know you are ready. Okay, 1.2 says, which one of the formulae below represents an alkane? Okay, now we're given molecular formulae, so to dispel the nonsense, it's going to be the general formula. All right, so this is the general formula for alkanes, and of course you may not remember. Just take the basic alkane, which is methane, and write its molecular formula. It's going to be CH4. So can you see C is 1? Then we can say H2 times 1, that's 2, plus 2, that's a 4. So it really speaks sense in terms of that formula. So we know we are ready to answer. This is a standard grade question, by the way, but again, slightly leaning towards the higher grade portion of things. So C2H4. Now this is just 2N here. That's an alkene. No. C5H10, again an alkene. C14H30. Now 14 by 2, that's 28. 28 plus 2 is 30. Indeed, that's the one. Once we find it, we go for it. Again, why would this one be wrong? This is C8. We can say this is CnH2n. That would be 8 by 2, that's 16. But now we subtracted 2, so this is alkynes. All right, so please, again, guys, if you don't remember this, go and check the general formulae for each homologous series and be able to remember it. Try to find a way of remembering it if it is forgotten. As you can see, my strategy when I was you, it was to always look at the most basic of the molecules in those homologous series, then try to formulate the general formula and then answer the question easily. Okay, the next question says, consider the organic compound below. All right, so if C 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, always consider the bands. So if each one of them is 4, then it's safe to take the straight chain right there. Right, and if we are to name it, so we want the longest chain, so it's the 4. It's a 4, but we can say it's a 4 carbon chain. Yeah. Anyway, we need the IUPAC name. So what do? We've got these substituents or side branches. Now we need to number our carbons so that we are closest to the branches. So it means this must be carbon 2 from this end. Right. because if we come from this other end, it would be carbon number 3, and we always want the number of carbons to the side branch or the first side chain to be the shortest from one end. So basically this is going to be 2,2 dimethyl butane. And again guys, this is either you know or you don't. Otherwise there's no manga business. If you don't know, this is something to revise. IUPAC naming of organic compounds. So this is an invitation from this review that, look, first I need to know functional groups of all homologous series. 2, I need to know the general formulae for all molecular formulae of these homologous series, and of course to check which one is which in each homologous series. And of course I need to know how to do IUPAC naming, because this is always the exam, guys. It never changes. All right, so if again these things you're comfortable with, you know you are ready for the exam in a way. Now 1.4 asks, activation energy can be best activation energy can be best described as minimum energy required, well, to cause effective collisions. That sounds right, because there's no turning back once we reach the activated complex. This is when we really reach activation energy, right? Make reactant molecules collide. Well, collisions, yes, but it's not made by the activation energy. They can collide, but ineffectively, because if the collisions have energy that is not sufficient to reach that of the activation energy, those collisions will essentially be not effective. So this one, not quite. Change the orientation of reactant molecules, not necessarily. Increase the kinetic energy of reactant molecules. It does not increase, so no. I would choose A as the best answer there. The rest doesn't make sense. All right, which statement is correct for a system in dynamic equilibrium? Now, these are the big topics in chemistry. Dynamic equilibrium. First of all, what are the prerequisites for a system to go on dynamic equilibrium? We must have a closed system. 2, we know that the rates of the forward reaction, I'm going to write FR, and the reverse reactions, I'm going to write R, are equal, right? They are not identical. I hope this is clear, guys. The rate, meaning the speeds at which those reactions are occurring, is the same, but the yield from those two, when looked at separately, may not actually be the same. So be very careful of such statements. They are very, very, very tempting statements to overgeneralize, and you end up in trouble. Now, of note is that in dynamic equilibrium, energy is free to enter, or we can say energy freely benifuna ukubhala kakuhle ke tana ngokuyaniphapela bona ke tsayiyeka, freely leaves and enters the system, right? Just remember that energy can leave or enter a system in dynamic equilibrium, all right? Just remember that. Again, a good demonstration is the effect of temperature in equilibrium. Great. Now, let's have a look at what are the options now. We want the correct answer. We are told here that all reactants are used up. They never get used up because the forward and the reverse reactions are still occurring, and that means we are forming reactants as well as products, so nothing gets used up. The forward reaction is equal to the reverse reaction. Well, this is tempting, but the problem is that it just says the forward and the reverse, and we know that those two are not in magnitude okay, but the rate at which they occur is what is equal. So what is missing is the rate. So as a result, it's a partially correct statement. Now, all substances in the reaction are of equal concentrations, never equal, but constant. So this is wrong. The concentration of the reactants and products remain constant. Yes, indeed, that is true. So this is D. Again, this is a question that could really cause problems, especially for option B and C. These are often mistakes students make when thinking about equilibrium, because remember, if you read without understanding, these questions will throw you off. Be very careful. All right, so initially for 1.6, a certain amount of gas P was placed in an empty container. The hypothetical reaction reaches equilibrium in a closed container according to the following balanced equation. So 1 mole of gas P somewhat transforms to 2 moles of gas Q. We can easily say gas P is an unstable gas. It quickly breaks down to this. Take, for example, dinitrogen tetroxide and nitrogen dioxide gas. You can find, proportions of the two if you put nitrogen dioxide gas in a container. So it's something similar to that, all right? Or perhaps it was heated, we don't know, we don't care. We are told something that delta H is less than 0. Now remember, when delta H is just put without a qualification as to for which reaction is it for, it then means this is the forward reaction. Forward reaction is exothermic, right? And this would mean the reverse reaction is endothermic. Because these always oppose each other like that. Great. So we need to know this. Now at time t, the temperature is increased. Okay. Now we know an increase in temperature favors the endothermic reaction according to Le Chatelier's principle. An increase in temperature favors the endothermic reaction. And this would mean the reverse reaction. It means we are going to favor the production of gas P. Great. So this is certainly a higher grade question, especially seeing that there's graphs to interpret. Now, of course, this one you need to spend some time and you need to synthesize knowledge around it. All right, so it says which graph below best illustrates the resulting changes in the rates of the forward and the reverse reactions after the temperature is increased. Well, we can see that this is the forward reaction, but now how do you know this is the forward reaction? How do you know? Because it starts off at a higher rate and then decreases to an equilibrium rate, whereas the reverse was not initially present, but it catches up until it reaches the equilibrium rate. So don't be fooled by the dashed line being shown on top, because we know that in most textbooks and study guides, the reverse reaction is normally represented by the dashed line. But here the examiners are trying to see if you actually understand why you would decide that this is a forward reaction against this is a reverse, if at all we used solid lines for both. Okay, so don't be fooled by the dashed lines. Now let's see, they reach equilibrium here, but now we said, by the way, temperature increase will increase the two reactions, right? Because temperature increases the rate of reaction, so both reactions should increase, but it favors the endothermic one. So we can say here both the forward reaction and reverse reactions will increase, right? But the endothermic reaction, which is the reverse, is going to increase the most, right? Maybe let's just use a simple arrow there. so that we can see that the double arrow means, so it should increase both, but the endothermic one is going to increase more, right? Now what we see here, the forward reaction is increasing sharply while the reverse reaction gently decreases, and this portion here is not representative. Come to B, we see that this is the forward reaction because it starts off high and then decreases to equilibrium. This is the reverse reaction, it starts off low and increases to an equilibrium rate. Now we will see that certainly in this segment, both reactions increased because an increase in temperature should increase the two reactions. But guess who is favored? The one that is favored the most is the reverse. Can you see the reverse reaction is now on top of the forward reaction? So there's a reversal of that equilibrium in a way. So this is quite what we want. If we look at this one, C, well, similar setup, and then they increase both in a acceptable way, but the problem is that the forward reaction is still on top, meaning it was favored, and that's not the case. And then D, we see that they both increase, but nothing seems favored here. This is what would happen if we had a catalyst. Please note D, because a question can be asked that draw this when a catalyst is added. Please know these things. So this is certainly a good question. Of course, B is the best here. Please understand these kinds of questions. You need to understand more. A bit of synthesis is very necessary in answering adequately. 1.7 says reactions 1 and 2 below have equilibrium constants Kc greater than 1. Okay, so what does it mean? There's more products than reactants. So it means these equilibria lie far to the right than to the left. Okay, so this would be more like ionizations of acids and bases. Okay, remember such things. This should have been Ka, but the examiner is trying to fool us into not seeing that these are acids and bases by just saying Kc so that you don't realize, because this should have been Ka. So when you're comfortable with the knowledge, guys, trust me, no trick can twist your neck at all. Okay, we've got acid, or not necessarily acid, but I know it's an acid now because this is a base. So this is going to be acid H3X protolyzing the bicarbonate ion there. And guess what? We get carbonic acid. And this is a weak acid. Carbonic acid is a weak acid. Well, that's fine. And this is a weak base, the bicarbonate ion. Nice. Now, this is an acid-base reaction. So obviously, this guy protolyzed that one. So in essence, it is an acid. So we don't know whether it's a strong acid versus a weak acid. We don't know as yet. Then we see that the oxonium ion here, this is the strong acid. This is the strongest acid you can find. Okay, it's a strong acid. It reacts with this H2X minus, which is a base. We don't know whether we can say weak or strong at this stage. And then this goes on to form water and H3X. Now, since H3X was an acid over there, so we're going to write it as an acid. And then this should be a base, and water is a weak base. Okay, good. So this is what we can understand from just analyzing what we are given. Again, this is one of those higher grade questions again where you can't just answer. There's a lot of thinking that is necessary here. Now, based on the reactions above, the acids in order of increasing strength from weakest to strongest are. First of all, let's see options that list acids. This is an acid. This is a base in our reaction, so this option is out. Good. Now, these are all acids. These are all acids, all acids. But now let's check the order. We know that the oxonium ion H3O plus is the strongest acid. So these two stay, but this one goes because we cannot have carbonic acid as the strongest. So this is already wrong. All right. So elimination sometimes, guys, will assist to some extent, of course, but some knowledge needs to kick in as well. All right. So now let's have a look. Fine. We know carbonic acid is a weak acid, but now we don't know in relation to this, what can we say? Now we look at that reaction of this acid H3X. We saw that it yielded a weak acid there. And there was a weak base here reacting with it. Now we don't know what to say, whether carbonic acid is weaker than that or what. But what I do, I often just take a model of an acid that I know is a weak acid, CH3COOH, ethanoic acid. I react it with a weak base, water. And let's see what happens. We are going to have H3O plus CH3COO, the ethanoate ion. But now we saw that we produced an acid, so to speak. So it looks like we are reversing the roles. Now we're saying this is the right-hand side. Of course, this is reversible, right? So we're going to say, well, this is the left-hand side now. We're reversing the roles. And this is going to be now our right-hand side. Seeing, I'm trying to draw some model here to try and understand, or at least to inform my decision of choosing against one, choosing one against the other. Now let's have a look. What do we have here? What we've got is that this friend of ours is a weak base, we know. And this friend is a strong acid. Great? Yes. And now we go on to the other side. We're forming a weak base and a weak acid. So essentially, we saw that we produced a weak acid when we reacted a weak base and a strong acid. And we saw that we get a weak acid. I don't know if we can say this is a rule or not. All I can say is that for me to produce a weak acid, and I know I used a weak base here, this must be a strong acid, right? Whatever it is, it will certainly not be stronger than the oxonium ion. So we can say, okay, we can take the fact that this is a strong acid. So essentially, we will then understand that B is our best answer. Of course, with hypothetical equations like this, it's not so easy to be sure of the answer given. But you have a fighting chance, because as you can see, if you can try and align something and try to read it in a way that would be perhaps similar to what we have, then we can perhaps try to say, well, science doesn't lie a lot. So similar things are definitely occurring in a similar way. So yeah, again, guys, I'm not so sure about 1.7's answer. But as a student, these are the things I used to do. And this is how I used to score hectic marks, because, you know, at times you don't feel confident of that answer because you will never know until you see the memo, right? But you will see that your strategy is actually solid, because these are not the things you will be taught in class, I promise you. If you are taught these in class, then you're the lucky one. Remember that. All right, excuse me. Now consider the cell notation for a galvanic cell below. Now a galvanic cell means spontaneous reactions. Right, so it's nickel going to nickel ions. So this is the anode, half of the cell. And of course, this is going to be the cathode, because we're seeing reduction of hydrogen plus ions into hydrogen gas. And of course, what is the role of platinum here? Platinum is an electrode, because this is an ion. Whenever we've got an ion, not a solid, because gas, okay, maybe let's say a gas or an ion, because what pushes us around is the end result of reduction. If reduction doesn't yield a solid, we often need what you call an electrode, because we need something that can conduct electricity. Carbon can be used as well. All right, not a difficult thing otherwise to figure out. So the question says, which one of the following half reactions takes place at the anode? We know that at the anode, oxidation takes place. So we know that oxidation. Now oxidation means after the bridge, we should be shedding electrons, however many those electrons are. So we shed electrons after the bridge. So let's see, do we see something like that? That is reduction. This is oxidation, but now the hydrogen gas is the cathode, so it undergoes reduction. It's wrong because of that. Otherwise, this is proper for oxidation. This one is reduction, and so this is oxidation. Again, this is essentially a standard grade question. It just says one needs to know how to read these things properly. If not quite sure what to do here, consult the standard reduction potentials. That table will tell us the position of the hydrogen plus to hydrogen gas is higher than the nickel one. And we know that the one that occurs below is a stronger oxidizing agent, a stronger reducing agent than the one that is higher than 8, which is more likely to be an oxidizing agent. Again, if you don't know this, then too bad for you, friends. But this again says electrochemistry needs to be revised, and there's a lot of technical factors there. It's not difficult, but it's technical in nature. So one needs to really revise those technicalities and know how to use the standard reduction potentials. Now 1.9 says, which one of the following is applicable in an electrolytic cell? Okay. Reduction takes place at the anode? No. It's oxidation. It doesn't change for both galvanic and electrolytic cell. At the anode, oxidation takes place. The only switch is that the anode is the positive terminal, as opposed to being a negative terminal in the galvanic cell. It is otherwise going to have oxidation taking place. Oxidation takes place at the cathode? No. It takes place at the anode, but the cathode this time becomes the negative terminal of the battery. Okay, it uses an alternating current. Well, is it a question of which power supply that we use versus just power supply? I'm not too sure. A battery is used for the cell to function. Well, again, must it be a battery or must it be a power source? I am not too sure about this one, because C and D for me, they're of equal magnitude. If you chose C, I suppose you should get a mark. If you chose B, D, you should get a mark. But I am more convinced of D, because in our textbooks and study guides, a battery is mentioned more often. And I have hardly heard or seen an AC power source specifically being mentioned. But we've seen cells of a battery, meaning it's a direct current. I'm not too sure about an alternating current, because yikes, that's the one. But if you saw some questions that never specified a battery, it would just say a power source. And an alternating current is also a power source. So I would say, well, I'm not too sure about C, but if anyone chooses it, I wouldn't mark them wrong, unless there's something in the curriculum guidelines that is specific about this issue. Again, these are the questions that makes you think, okay, now failing to know better than what I see and what I know. This is why I say guidelines is what you would do if you don't have anything better. Then you gravitate towards them, because if you do anything less than the level of the guidelines, then obviously you are going out of the window, right? Yeah, you become garbage. So let's see. Maybe C is acceptable, but I would certainly choose D, because now on the books, I know a direct current is often used. But as to the technicalities of whether is it alternating versus direct current, well, that's a different story now. This is again one of those questions that you would say, okay, I'm going to flag this because I need to find out. Is it? Now find out, students. When you study, don't just answer questions and then check the memo. Sometimes you get yourself some homework, if you would call it homework, or some bit of work. Find out whether the power source matters or not. I wanted to write nicely, but now this thing is always find out whether, okay, let me try to write better. Find out whether a specific power source is a necessity. A necessity, right? Now we are talking about direct current, DC, versus alternating current, AC. Now these are the things you want to quickly check, because remember, you are studying. You're not just, going through the motions and answering these questions. Mind you, what are the chances of seeing these questions again? Maybe not necessarily very high chances, but if you see these questions again, they will have been modified to some extent, unless you are really lucky. The province decided to perhaps repeat these questions because they're a little bit older, so they know students often forget about those questions, so they can be brought in as they are. But an examiner who's careful can actually borrow an idea rather than to repeat the same question, because it's unacceptable to repeat questions. Because what about those who did not see that question paper? You're giving advantage to others while you're sinking others. Not fair. There shouldn't be repeats, in my opinion. Which is why students must not have access to question papers, by the way. They must not have access to question papers so that we can keep a pool of questions nicely. Otherwise, with this way, then the questions often get crazier and crazier. And you can attest to that. Those who wrote the midterm exams, they saw that, yeah, the questions are getting crazier and crazier, because the standard is that we cannot repeat. Because if we repeat, we're giving an advantage to those who were shown the paper. And now there's going to be cheating going on, because some teachers know these things because they have friends of those who submit questions. So they would know that there's a question from November 2019. And then they will make sure their students practice that paper, because most of the questions are going to come from there and they will repeat literally. But now what happens to those in the same province who did not have that inside information? So it becomes very, very bad. Because I know now teachers are in the quest of seeing their students hitting 100%. So they don't care whether these kids know the work or not. All they care about is these kids showing up with 100%. Now they do things that are rather regrettable. Anyway, let's not go there. You know how I am when I get to those kind of things. Because really, guys, you would be a fool to really turn a blind eye onto these things. They are happening. Anyway, let's go. 1.10 says the flow diagram below shows 4 stages, A, B, C, and D, in the conversion of sulfur to sulfuric acid. So this is the Ostwald process. Is it? No, contact process. This is the contact process. But you guys don't do this inorganic chemistry section, which is good, but I don't know why, man. Your curriculum keeps on being confused. Why take this out? Why? Let students have it all, man. We're not here to create weaklings. We're here to create scientists. Now, we can't just take things away. In fact, we should be adding things instead. because now the more information on these topics is available, the more we should add new things. But add rather than subtract, because it means the common knowledge, they should know it. There's no excuse for them. But the new stuff, yeah, they wouldn't know it, at the tips of their fingers. And that's what we want to examine. Can they move along with the science? Anyway, guys, the question says, okay, we've got sulfur going through stage 1 into sulfur dioxide gas. So this is the oxidation of sulfur in air. We just burn it in air. Then we get this one, and then we've got stage 2 when we form sulfur trioxide. Then stage C, it forms oleum, and then it comes down to sulfuric acid. By the way, that oleum, I think it's sulfurous acid, but it's another name for it. Doesn't really matter after all. So it says, at which stage is a catalyst used? Again, this is a standard grade question, if not a lower grade question. It's either you know or you don't. So obviously the second stage is what we call a catalytic oxidation of sulfur dioxide gas. So this is B. And at times they used to ask what catalyst is used. Is the contact catalyst vanadium, or we can say divanadium pentoxide. Okay, it's vanadium pentoxide. That's the contact catalyst. And so we termed this the contact process as a result. All right, so please guys have a bit of background knowledge, and those who are in the channel as subscribers and those who really follow what I post in the channel, already this should be easy. Although it's not part of the exams, it may not be asked in the next exam, but remember, know things even for the sake of knowledge. You don't need to know for an exam. Need so that you know. You need to know so that you know enough, okay? You don't just need to go and pass an exam only. That's bad if actually that's the approach by the student. Anyway, guys, I don't want this video to be too long so that you can actually watch it within reasonable time and really get to see the highlights that I had to point out as we went along answering this question so that you can revise. As I often say, MCQs are exactly what you call, it's a window into the long questions, because the long questions are built from these questions and nothing else. So it's more like repeating the same thing. So this is why when you fail, we fail you with a happy smile in our face, because we know that essentially the student is careless. You cannot be asked two things. I mean, you cannot be asked the same thing twice and sometimes 3 times and you fail. Remember, the 2 techniques of asking is to try and remind you. You may have skipped a question in MCQs. When you get to the long questions, it will be asked in a different manner that helps you to remember what you had probably forgotten for the MCQs, and vice versa. Sometimes you may find it easy to answer on the MCQs, and on the harder questions, you can go back to the MCQs to just remember something. So these things are interrelated. So never ever treat these questions separately. The whole paper is a unit, and do not take it into parts. Remember, it's a whole thing. It's a whole thing. It's not a partial thing. Spare that we divide it into subtopics, but they are all chemistry. All right. Anyway, guys, goodbye. I'll see you in the next video.